Welcome to the roundtable. My name is Ignacio. I'm now SICAM director, and I will say this is also a workshop organized within as part of SICAM activities. And it's a pleasure to come here to the end of this workshop to have a broader discussion among some of the panelists that we have here, Gerhard, Thiel, Sansom, and Mario Kinapi, that you have heard them also as lecturers. The goal of this roundtable, which is very much in the spirit of what we foster within SICAM, is to move beyond the usual exchange associated to presentations and to create a moment that is more where everybody can intervene and that allows to address open questions. I've been hearing about challenges, and actually this workshop has brought together people working in quite different areas, going from ion channels to nanopores. We have heard theoretical advances, the development and exploitation of modeling algorithms and methods, and then also state-of-the-art experimental situations. So I think it's a good moment here to have the possibility to exchange views and also have questions about challenges and also about interrogating how different approaches can be complementary in the view of where we are. As Alberto explained, we will organize this dynamically. There will be a short presentation by the three panelists, and after that we will then open the room for interventions from all of you. Unfortunately, we are not face-to-face, so in order to organize this, you should indicate in the channel, in the public chat, that you want to ask a question, and then I will, after the presentations, I will mention the name of the person with that wants to put the question, and as Alberto said, you can activate your mic or your camera, so that then you can pose the question live and make this more interactive than just a set of questions that I can keep on reading. In this way, it's not only just asking a question, but there can be more a bit of a dialogue depending on how panelists will be responding. Okay, so as I said, we will start by these short presentations by the three panelists. I don't know if you have any preference, otherwise I can go by the order I saw you in the screen. And Mark, you want to start?
Okay, I'll try to share my screen. Too provocative. So it was a very stimulating and interesting meeting, and I greatly enjoyed it, particularly bringing together the more biological and the more physical aspects of channels and nanopores. But at times I felt a little bit of a feeling of deja vu, and I don't know how Benoit feels about that, because going back to the start of the century, there was the first KCSA simulations. I went back and checked, and I think Benoit was one of the first, and then there was Paolo Coloni, and Chung and Akvist and others. And so I thought, well, we've had 2 decades of simulation studies, and we've almost agreed on mechanisms of permeation and selectivity. So I think that tells us that it's we're in this for the long haul. We don't get the answers immediately. But I think there's been definitely substantive progress, and on the methodological side, there have been great improvements in simulation methods, in computational power, in sampling methods, improvements in force fields, and I think also what we've seen particularly is also developments in underlying theory. We've looked at a lot more channels, and we've seen that that's been driven by experimental structural biology, and particularly the past few years by cryo-electron microscopy, which has been a remarkable development, not without its challenges, but certainly changed things. And I think one of the things we saw in both some of the experimental and some of the computational talks was a shift in emphasis maybe, or a beginning of looking in more detail at modulation of channels by lipophilic ligands and looking towards novel druggable sites. And so in terms of what's in the future, so this is where maybe I'll try and provoke a few thoughts or comments from others. What's left to do in terms of the basic science of channels? Are there big breakthroughs out there that we can make, or are we now at the stage where we're asymptotically approaching a good understanding of structure and function? And I can see we could do more in the biology. We could take kind of detailed understanding, particularly for potassium channels, and try and achieve that level of understanding for, say, all the channels for which we have structures. And I think maybe on the physics side, or physical science side, we can try and get a better understanding, in-depth understanding of design principles and pores. I think the other thing that, as I feel has shifted or is likely to shift, is maybe a change in centre of gravity from the basic principles, the basic science of channels, to actually doing things with that understanding. So on the biomedical side, I think particularly looking at allosteric sites and whether we can exploit those for therapeutic modulation of channels. And from the nanopore side, I think what I really would love to see is rational design of function. And I think both of those have got challenges, and the two I think we've had mentioned that I can think of is, it's great to say, well, we now understand channel structure and dynamics, and we can start to talk about allosteric modulation, but even, I can't remember which speaker mentioned it, but even just trying to get accurate free energies of binding of lipophilic drugs is going to remain challenging. And then I think we heard a number of very nice talks, both on the theoretical side and the experimental side, of manipulating the properties of pores. But if we're going to do that for technological applications, will it be modulating protein structures, as in the alpha hemolysin based devices, or are we going to build new things? And maybe that's something we didn't hear quite so much about novel synthetic structures for nanopores. Maybe that's for a good reason. Maybe we don't know enough yet to build those things in a controlled manner. So I think the two questions big questions are there big fundamental breakthroughs still to be made, or are we at the stage where we have a reasonable confidence in our understanding, and how are we going to exploit that understanding? Okay, I'll shut up now. Those are my limited thoughts.
Yeah, thank you very much, Mark. I don't know if Gerhard, do you want to?
Yeah. I try hard. I don't know why it's not working. We had this problem yesterday.
Yeah.
Do you see anything?
No.
I try once more, and if not, I just
Okay.
okay. Now I see some development.
Yes.
Can you
Okay.
see the screen?
Well, we see the video chat of the presentation itself.
Maybe you have to share the other screen.
Yeah, since as if you are sharing.
Right. We only have one.
No, we are seeing the same.
I'm sorry. I can just.
Sorry, Gerhard. If you want, you can share your entire screen as you were doing,
Right.
and then just click on your presentation, on
Okay.
the window where you have your presentation.
Okay. Great.
Thanks.
I don't know what went wrong. So Rebecca, are you doing something now, or do I have to do something?
I think she said that you can do that. Just like share the screen as you did, and then go into the presentation mode. That's what she meant.
Yes, click on the presentation. So you were doing the right thing.
Yes, Gerhard.
Are we good now?
You didn't share yet your screen. Click on the bottom as you did before. Share your entire screen, and then click on the presentation. Select the presentation. Okay.
Now presentation. Yeah.
Now presentation.
Yes.
That's perfect.
That's
Okay.
it. Perfect. Yeah.
Okay. I also enjoyed this meeting a lot because it gives a lot of sort of new ideas for how to advance the field. I'm coming from the experimental side, and we're measuring single channels. And this is still the best method for single molecule analysis. So you can measure with high precision, very long time series of the activity of a single protein. The problem is that we're measuring our activities on the time frame of milliseconds and seconds. That's the sort of the fingerprint of single channel activity. At the same time, these very precise measurements, they are complemented by more and more high resolution structures on ion channels, the KCSA, and many of them which have been following up. This again is complemented. I mean, the structures are static pictures, and to bring dynamics into static pictures, this is what molecular dynamics does. So the molecular dynamics is able to monitor the movement, the conformational changes on a small scale in a protein, and they can see the making and breaking of salt bridges, of hydrogen bonds, and whatever. The question now is, and this is, I could now refer to Ben Arus' talk, saying when you measure a single channel, you may measure this kind of opening of the channel. But the thing is, we want to know what kind of conformational state in a protein we are measuring. And we want to overcome something like this, which is a statement, a very recent statement of a reviewer on a very high impact journal, saying that MD simulations are basically there to generate a hypothesis, but not enough to validate experimental data. Our vision is that we have experimental data, and we want to correlate the movement of a structure of a domain in the protein. We want to correlate this to either this long close time, short close time, or the immediate close time. To get there, I think we can work on different levels. We can, and this is a challenge for the electrical engineers, for the physicists, to improve the recording systems. There are already sort of endeavors in the lab of Ken Shepherd using CMOS technology, reducing the capacity of noise. And what we get is we get to resolutions in the range of 1 microsecond. So we're close to what you see in ND simulations. So if the ND simulations, let's say the lifetime of a solid gauge that you can monitor in the simulations, maybe from the lifetime of the ND simulation, we can really directly correlate this to a functional signal in what we measure in the channel. And I think this will be a great advantage of really making a complete picture between function and structure. And then the last message, and also coming from sort of listening to all the talks in this meeting, is, as Feynman said, what I cannot create, I do not understand. We understand a lot on the structure function correlates on proteins now, ion channels. And the idea is we can start to build proteins which are sort of reflecting the knowledge that we gain from our endeavors, and to, for example, to introduce new gates into channels. And then we will also understand how a channel protein works. And we can even implant this or sort of craft this knowledge into solid-state nanopores. Maybe we can introduce receptor sites in these nanopores, link proteins, and sort of really combine the knowledge of engineering on proteins, on channels, and crafting this information onto solid-state nanopores. And I think with this I can end.
Yeah. Thank you very much for these thoughts. I'm sure it will serve to the following conversation, discussion. So I'll move to the third panelist, Mauro. I'm sure you will have interviews.
Okay, can you hear me?
Yes.
Okay, so I would like to thank you, organizer, and my talk will be very short because I just a couple of really provocative questions that sometimes I ask to myself and then I ask to all the audience. My background is in simulation. This may help you in understanding why I have such kind of provocative question. Did you see my screen?
Yes.
Okay. So in essence, we all know that accurate measurement at nanoscale are quite complex, and a lot of quantities cannot be seen in experiments. In simulation, sometimes you can somehow, let's say, adapt to the protocol to calibrate the force field to try to reproduce experimental data. A typical example that I have in mind is when we discuss about solid-state nanopores, and for instance, you have to model the interaction between water and solid-state nanopores, or solid-state membrane in general. And it's not unusual that different simulation methods give different results that may support a different theory and different hypotheses. So the question for myself and now for you is that is it a solid scientific process, or sometimes we are just fitting or cherry picking data? I mean, this is the first provocative question. The second one instead concern the interaction between synthetic nanostructure and living organisms. And this is, if you want, more related to the fabrication process and to the experimental part. I was wondering if there are any opinion in the audience on the possible major environmental and health issue that can be associated to this interaction. And those are two of my questions for the roundtable.
Okay, thank you very much. So thank you to the three panelists. I think this already are a number of points that have been raised, open issues to discuss. I remind to everybody that you can contribute to the discussion or bring new issues simply by typing in the public chat your interest to pose a question or to contribute to the discussion, and then I will give you the word. While we wait for the first questions to arrive, I don't know if there is any feedback. I mean, you have heard to each other, between the three panelists. Is there any thoughts that have come from each other, provocative thoughts?
I can ask Mark directly. So how far away are we from really relating simulation results to single channel recordings? I mean, to identify a wait time with a conformational or with a physical sort of activity in a protein.
I think it would still be challenging to try and map a structure onto a conductor accurately. And I think that may reflect limitations on force fields, even for channels where you're not having a large degree of dehydration alongside ion permeation. I think that's still challenging. So I think there's still some force field work to be done. I think Benoit's got a comment in the chat on, is that Benoit? Yeah, on force fields.
Yeah, Benoit wrote that he wanted to make a comment. So Benoit, if you can unmute or just activate the camera and then you can pose your comment. Yeah, there you are. You have to unmute yourself. Yes.
I'm unmuted.
Right, perfect.
It's very nice at least to see. Mark, I haven't seen you in a long time. The beard is really very good. I don't know how long.
Thank you.
But
It's to compensate from the mic. It's migrated from the top to lower down.
Oh yeah. Well, you look good.
Good to see you.
For the force field, I think I would say that if you calculate a process and a free energy difference between two conformation or whatever an event, and obviously these force fields are approximation, and even if you went to full Corporinello simulation all the time, it's essentially a kind of a force. Even if you did like admonition at these levels, it will always be an approximation to reality. If you compute something and you get, let's say, 12, but experimentally they measure 10, then it's a quantitative difference. Then, you could tweak it to get the number that they get. It's probably not, I don't lose sleep over something like that. I think if you calculate something and you see a process that happens and then somebody else goes and do a simulation and see the process does not happen, then it's a yes or no. Now you start to bifurcate into, is this absolutely for real or not for real? Like the dehydration of regions, something like that. You do it with STC or tip 4 or tip 3 or polarizable water, and you start to see this thing is not happening or happening. It's still obviously a quantitative thing, but then it's probably worth exploring at least the sensitivity of what you observe with respect to the force field, because every force field is going to be imperfect. So you'd like to say, like, well, what is, and I would say, for example, the hard knock mechanism of permeation is a bit in that realm, in my opinion. It's like, so is it versus the knock on? Like, are we in a world where we know for sure the qualitative behavior given the force field? You could change the force field by plus 10%, minus 10% on different parameters and try to see, do you really observe a phenomenon, yes or no? And so to me, that's more like where the force field is really a critical issue, is when you really want to know if something is going to happen or not happen. If it's just a quantitative shift, then that's not dramatic. That happens all the time,
Yeah. But for example, when I come to my point on different gates, I mean, let's say a channel has two closed states, and they are sometimes one order of magnitude apart in their lifetime. So if one measures 10 and you simulate 12, it doesn't matter. If it's not 120, which means like this is enough to say these two processes, they operate on the same sort of time scale, and they must be the same. If you have the same protein and you have measurements, you have simulations. At one point, they must come together.
And perhaps one thing that pertains to that is that, you know, there's really two trends in our world of simulation. Some people do enhanced biasing and stuff like that often, and other people tend to run more a vast amount of unbiased data, and they both have plus and minuses. I think that a lot of processes, of course, you tend to get the more objective reality of your model if you run unbiased data and then you observe just the spontaneous repartitioning of processes and events and whatever. However, you are a little bit vulnerable to the accuracy of the force field. If a process can happen, you know, 10% of the time experimentally, and you run it with your force field and you don't see it, well, it may be that it's just that, you know, the free energy of that state you're trying to capture is just a little bit less favorable by a handful of kcal per mole, and now the probability has sunk from 10% to 1% or 0.5%, and now you don't see it. It just doesn't mean that the model is completely wrong. It's just quantitatively you're just a little off, and now you won't be able to see it. So I think, you know, it's nice to be able to quantitate why things are happening at different levels with different computational strategy to bracket with more confidence what's happening. You know, something Mark said earlier in your talk that, you know, that it is true that the first KCSA simulation, Paulo was the first one in biochemistry. There's the 1999 paper, and he didn't think it was the first paper. I think Johan August perhaps was the second. And I guess we're all a little older than we were 10 years ago. And it is true that, you know, maybe there are some, it's the sad part with these conferences, I don't see the faces of all the young people in the room. Hopefully there are young people listening to older people like us, you know. But I remember a Gordon conference some years ago, I think Mark, you were there, where Bertil Hiller was saying, you know, here are the big questions and this is important. And he was basically saying, you know, I think he was an older man, so older than us, you know, and then saying what is really important. And it's true, when you do science, you have to work hard every day, and there's a certain feistiness that sort of is a bit unavoidable, and every paper and every calculation is important. But when you start to back off and you realize that it takes 20 years to develop a sense of consensus and accepting some result. And just recently, I published a paper with Giovanni Ciccotti on the history of the first paper that Martin Karpus did on the H plus H2 reaction and the context of that. You know, in science, there's a bit of both. There's the relentless work that you have to do on an everyday basis to push the thing forward. But the big message is really that it takes a long time to do something meaningful in science. And you need a bit of both mentality. And, you know, it's unavoidable that the long time scale, you know, a lot of problems, you know, our entire life is dedicated to push things by a little delta X forward. And at the end of the day, you know, you should feel good that you contributed to do that. And this is just the work that we do is now more and more the result of the contribution of many people. You know.
Yeah, we don't want to discourage the young people, but it's about one career to get to the stage where you could watch an iron going through a hole. But it's still a step forward.
Since you were discussing this issue of force fields, I mean, I don't know if putting it a bit more in a wider context. Gerhard had this sentence coming from this review, the fact that molecular dynamics are good to generate hypotheses but not to validate experimental data. After all these 20 years, do you think that force fields is like the main bottleneck to achieve that validation, or that is more or less clear according to your discussion. And what would be then the next sort of challenge to be able to achieve such validation in comparison to experiments?
I would say that there are many things that give you a bad surprise in a computational project. I think the inaccuracy of the force field is not the number one nightmare. I think it's more lack of sampling. The fact that you start somewhere and you basically, your dynamics, or even if you do a collection trajectory, you're going to drift away from your starting conditions by 10 microseconds, perhaps 100 microseconds, but not much more than that. And so the lack of sampling is really the real nightmare. Now, the thing is, computers are getting faster, GPUs are going to be getting cheaper, and molecules don't move slower. They move at the same rate. And so, ultimately, we're winning the war of the sampling, little by little. We're moving forward to win the war of sampling. And molecules are, 20 years from now, molecules will not make transitions slower. Maybe we'll look at things that are more ambitious, but we will definitely have completely conquered some type of motion.
Can I make a comment? I want to be provocative, but what you say, Benoit, is this not also true, for example, for cryo-EM and crystallography? Because, we are visual animals and we think what we see, we believe. But what we see is also going through a process of sort of the same thing that you are going through. What is in your case force field is in their case analysis software of identifying the densities. Because there's always now this claim that if you have a structure, it's true. If you do a simulation, you have to justify your force field. This is sort of my provocative question.
Well, I don't know, Mark, how you experienced that, but I certainly have felt that there's been quite a shift in the relationship of the experimental structural biology community with the rest of the biophysics community. And 20 years ago, you got one structure and everybody was just like, this was like the pinnacle, and everybody was looking at the structure. And as soon as you ran a simulation that was deviating away from that structure by 1 or 2 angstrom, everybody got nervous. Now, most experimentalists will often have somebody running simulation in their own lab, and they are not really, they discuss very freely. I talk with Eric Guo or Dan Miner or Krina and Mijan, many people. Experimentalists definitely realize that, this is the conformation I've captured in that particular crystal. This is not really, it's not a religion as it was 20, 25 years ago. There's much more of saying, if you run, maybe you try to crystallize a protein and you shoot your 100 crystals and you're going to discover that you captured maybe 5 conformation in these different crystals. People are less dogmatic about that than they used to be, much less.
To stretch Benoit's metaphor, maybe structural biologists have moved from being orthodox to liberal. And they can accept there are multiple conformations. And I think Benoit's right. I think one of the things that shifted as simulations have produced insights. I think our experimental colleagues are more interested in them. So I think there's much more conversation than there was 10 years ago.
Yeah.
And I think that will be that's one of the things that becomes more evident now with some of the advances in cryo-EM, because a given protein is straight away yielding multiple conformations, and so there's an awareness, earlier on that it's not just what one structure and all K channels look like that.
If there are no questions on the chat, I can also ask the two of you. Now the cryo-EM delivers these different structures of proteins. Are there tools, sort of computational tools, to really show how one structure acquires another one, and that is not a matter of sort of free interpretation of the author of a paper to say, put things in an order that is most suitable to the favorite hypothesis, but maybe chemically not sort of justified. Maybe you cannot go from this structure into another one because it's chemically forbidden. You understand my question?
Yeah. I don't know if anybody's ever tried that in computation, to say take multiple snapshots, put them in the wrong order, and then try and drive between them and say, I can't do it. So let's say you've got snapshots A, B, C, and you then try and do some fancy steering to go from A to B to C, and you've got them in the wrong order, and have you seen that tried, Benoit?
I've seen
Either by design or accident.
people have done movies. I think I'm blanking on the name, but on the ribosome, I've seen movies. I think even Andreas Engel has done movies, even on porins, where they did like EM structures of porins in different conformation, and then just like order them by similarity. And just saying, well, you must go from image number 1 to this particular image because that's the most similar. And so they would rank order the picture by similarity, and then have a movie like that. Now, of course, if you run molecular dynamics, you know that that's something that's encountered in a lot of. I don't know if Thomas Schutte and all the others, Gerhard Hammer, are still online, but just lumping together structures that just appear to be similar does not mean that they belong to the same dynamical class. It doesn't mean that you go from here to there through, like in a real dynamical trajectory. And that's often the challenge in doing Markov model, is to make sure that you thread through the microstates in the proper way. Because when you look at the microstates only through the image of less features that are not all the detail of everything. It's like you look at a subset of features. Things look similar, but in reality, they could be very different conformation, and they don't really communicate. So, GP. Who's GP?
Yeah, so there is a comment by Gonzalo Paulo.
Okay. That's a very thin machine learning technique, and certainly
Okay, go on.
Perhaps, yes. I think, there will be, there.
So this is Gonzalo. So
I think there will be, this is going to be a major undertaking, but I think it's possible to capture multiple structure by EM and then trying to link them together consistently through trajectories to make sure that, in which order these transformations must occur. I'm pretty sure that's a feasible thing. But this is not going to be a weekend's work. This is going to be very hard.
Okay. I don't know if you want to elaborate more, Gonzalo, on this.
Yeah. So recently, for me, of course, because I'm quite new on this field, as I'm just starting my PhD. But I've become aware of multiple new techniques of machine learning and also molecular dynamics that take into account that you need to change your algorithms if you want to access rare events. So, for instance, PET sampling techniques or metadynamics. And because these algorithms are starting to become more like black boxes, where you don't have to do the algorithm all by yourself. You can just use libraries. Do you think that because these algorithms are more accessible, more people will start to use them, and so a breakthrough will be seen in some kind of problem which was previously thought inaccessible, but now with these new techniques becomes accessible? If so, where do you think this breakthrough may appear? What is the problem that you think can be broken through soon?
You want me to chip in, or is it a question to me? Or?
Well, it's a question of both of you. I don't know who dares forecasting what's going to happen, but yeah. You can start.
I think, you know, that there's clearly, I mean, I have seen recently, you know, in the last decade, I would say, there's been a new way to look at simulations, you know, through the lens of these, I wouldn't even call that the Markov model paradigm, but it's more like a kind of a statistical mechanical paradigm of propagators and eigenvalues and slow modes and spectral analysis and all that. When you start to combine these very powerful concepts with machine learning, it does look like it may be possible to tease out objectively, with no prior knowledge, things that are going on in a system. Now, it's still probably necessary to have, you know, the mind to guide the questions. Because, for example, objectivity is nice because it's objective, but the problem is that you get the whole universe fall on your head also. Like if you do a full spectral analysis of all motion of the ribosome, they could, and then you say, I'm going to just pay attention to the slow mode. There could be a lot of slow mode in the ribosome that are absolutely of no interest to you because they don't pertain to the translation of the messenger RNA. And so sorting out these processes needs a little bit more human input. And that's why, I mean, Frank Noe and you know, Thomas Schutte have said that, you know, just at some point you reach the limit of just a pure objective spectral analysis of dynamics, because there's too many modes, and too many of the modes may pertain to things that are of no interest to you. And so there are some slightly more deliberate, more hands-on type of analysis where you would say, I want to know the pathway to go from the state A to the state B, and you get to pick which state you want to go from and to. And now you discover the proper statistical mechanical set of pathways that takes you there. And, you know, there's machine learning to get to learn that. And they're very data hungry. So this is not a trick to save computer time. By and large, it is not a way to save computer time, but they are very powerful method that you could be able to learn, you know, what really guides, what are the aspect of a transition that guide from one thing to the other. There is a comment like, are we making prediction? We are making prediction. Like, you know, everything I said about the herd channel at the end of my talk is not verified experimentally, at least from a structural point of view. So this is a prediction. If I'm wrong, I'll get beaten up by people in the future saying this was totally wrong. So I think, you know, there are new advances that are showing up on the horizon in the way things are being analyzed, and the very pedestrian way that I was raised in, you know, with you pick an order parameter reaction coordinate, and you do the potential of mean force with umbrella sampling, and you look at the transition along that. That is, you know, very 1980s, 1990s type of way of doing things. But people are moving away from that now, and it may be that this will open up into a new countryside, which has very, very powerful tools that are quite different, I think.
You wanted to add, Gerhard?
Yes, I still want to hammer on the sort of the perspective of the experimentalist. Ion channels are fantastic because you measure current. I mean, the ribosome, to see the translation of a mRNA takes forever. It takes about 15 nanoseconds for an ion to pass a channel. So nanoseconds, that's sort of the time regime of your guys' sort of simulations. Now, if from the experimental side, we come close to this 100 nanosecond kind of time in measuring and seeing the opening or the closing of a channel. You know, this, in my view, must be another quality in terms of relating things that you see in a simulation and things that happen in the real activity. So, I mean, just as a question, would it be interesting for you on the computation side to have data which are sort of showing single channel activity in the time frame of tens or hundreds of nanoseconds, tens of nanoseconds? So we're talking about, let's say, future developments. And this is something, you know, for the physicist, we heard a talk of Sophie, you know, things, what you can extract from noise, the solid state people, they make super small holes, which may improve the capacitance noise, so that we really, maybe in a few years, we are able to measure ion channels and we see the single ions going through. This must be, I think, in my sort of simple vision, the ideal system to correlate things that you see in a simulation and directly understand what is happening in the protein. Different from all the big proteins where you lack this very precise and very rapid monitoring.
Sorry, Benoit, you are muted. You're muted. Now, Benoit, yeah, you need to click the mic button. So
am I mute? You hear me? Oh, okay, so as I said, some things never change. It's hard to shut me up. But you know, looking at, for example, if you just have an ion channel, you say you look at the IV curve, that's the current. Predicting the IV curve is cool, it's nice. And if you get that done, that would be nice. But what it isn't at the end, like if you experimentally can measure the current as a function of time at a much higher precision and higher spectral resolution, the noise in the current now tells you things about how the ions are jiggling into the channels. Like basically the noise content of the current contains, it provides new information. Fred Sigwart looked at that. I'm not so sure there's been a lot of effort yet to utilize that, but it would be a very interesting thing to look at. And in principle, you could compute the noise from the jiggling of the ions. You have to use a correct, you cannot just have like a hard partition and count the ions across the partition. You have to calculate with the proper capacitive effect and everything in the system, but it's possible to do the displacement current correctly. And then look at the noise to see if you really get that right. That would be very interesting. This is also about validation, but it would be very, very interesting. There were some comments about, to Mark's sense about the liberal sciences. So I'm going to just ease out here and listen to Mark if he...
Okay. I don't know if...
I'm not sure what I was saying now, but I think going back to one of the questions about where we think breakthroughs might appear, we've maybe focused to a large extent upon the advances in our computational methodology, but I think one of the other things, and you sort of touched on it actually in your talk about the C-type inactivation, Benoit, by looking at in detail at different potassium channels, is we can either pursue more detailed or longer simulations of the systems that we know and love very well, or we can broaden it out and look at a much wider range of systems. And I think one of the things there in terms of, which motions that we identify are important, which ones are less functionally important, one way to tease that out is if it's functionally important, it should be conserved. And that's a very powerful tool that now, as we have more computer power, we can look to see whether we observe the same thing in other members of a given family of channels. So rather than just we have n equals 1 in terms of biological sample, we can look at more homologs and see whether something is conserved. And I think that didn't used to be possible because we didn't have the structures, we didn't have the capacity to go through multiple members of a family either.
Okay. So I think more or less, I mean, there were these questions by Fabio Cicconi, but I think more or less the trust and predictions that you touch on. And then, yeah, so I don't know, you have more or less also addressed the question by Fabio Franciolini from a different perspective. There is a question by Armagan Koser addressed to Mauro. I don't know, yeah, you can reply. It's about health. Technical.
Yes, it's a very interesting comment. Hi.
Hi.
And my curiosity on your comment is, which in your opinion can be the best material for biocompatibility, non-toxicity. So I mean, when we talk about hybrid structure, okay, they should work, but they should not be dangerous for the organism. And so, in my opinion, one of the open questions on this issue is exactly which can be the more promising material to such application. I don't know if, Armagan, you have any specific idea on this.
I'm thinking about a way of sensing and communicating bidirectionally. I didn't investigate yet the materials, but there are enough people working on the material like this body part itself or the prosthesis inside used in the body already. So one could also engineer their channels, pores, or the type of structures. But I don't know the material yet, but I see that as an opportunity, or I'm very excited about it. And for the environmental part, I would suggest to just using the power of nature or mimicking it to detect the diseases like corona or compounds in the environment, like point of care devices or things that you can embed it using the place that you need them. So that could be interesting from the environmental point of view. And I was thinking we have these, now we learn more about how the channels work, in my case at least. And I was thinking about the communication between body parts. It could be like what nature has, or maybe there could be other way of communication if we let the cells interact with the materials, or very wild thinking, but maybe in the future there could be other mechanisms also arising from this type of work.
Yes, and also another challenge, maybe the issue is that when you have something that is in contact with the living organism, I mean, nature produces your channel, but if you have an artificial part, you have to find a way to replace. So I don't know if one of the big challenge in the future can be also the self-assembly of synthetic structure to talk with biological part. I mean, I'm not expert of this, but I find that this is one of the big points in this hybrid issues.
Interface part, yeah.
Yes.
Yeah.
Okay. So maybe building on this last discussion, I mean, there has been a long discussion about how the field has advanced in these 20 years and the role that simulation has played, but then there is this question by Giovanni Cicotti about how to be looking to cooperation between more than one field of methods. I don't know if Giovanni wants to elaborate or we want to take it from here and say, I mean, in the initial presentation by Mark and Gerhard, there was this point about how much can we learn by looking or by the advancing nanopore research. I don't know if you want to build on this perspective. Or if, yes, hi, Jeremy.
I can surely say, although I have been forced to be a traitor in the sense I didn't participate essentially to the workshop, but my understanding of the, for reason I was forced to, there has been a push by this friend biologists like Benoit, Mark, etc., in the sense that the workshop was an attempt to prove that it was possible to go across, so to use the advances in biology for pores of other nature, and that all that could be in a very important interchange with methodological advances. And the roundtable should be an attempt to say in which direction advances can help, in which instead we have heard nice things, because they were nice, about ionic channel. But to close the roundtable like that is equivalent to say that biologists have done a push. And I don't permit to biologists to do a total taken of the power, because this is illegal. I am joking, of course, but I think it's important.
So my joking response would be to, if maybe one can understand why the biologists have had a push. If you look at the number of Nobel Prizes for chemistry that have been awarded to biological problems over the past few years, I mean, I think that, you know, the excitement is in the biology, and I think it's by studying the biological systems in more detail that you will come up with new ideas how to design nanopores. Otherwise, and I'm being provocative now, you just have a hole in some carbon.
No, I am not doubting of the interest and the importance. I am saying that we convened to try to do, in some sense, something not necessarily more, but different. And I am very sad that no one contributed what are the problems, the difficulties to the round table of the pore in inert matter, when it's not the biology the challenge, but it's just the brute matter that we have to control at very, very small scale. And also, I think that we could never penetrate this field without tools that go beyond the standard MD. And I was horrified by the question of the young PhD saying, but now that we have metadynamics, not my preferred tool, as a powerful tool to do rare events, now we can go by black box. If you go by black box, you find shit normally, because black box and not understood are really bringing good physics. And that's really a problem, that we must more and more become and produce good simulation theoretician to advance. And all that somehow was a bit in the scope of the workshop, and I would have much more liked that there was also that. But Mark is right. I mean, if he has to speak, he has to speak of major excitement, not of the one of the others. So was not a very attack, neither to Mark nor to Benoit. Moreover, I see an hand raised. I see an hand raised by Gerhard, yes. And I advance something. Also, the experiments were there because experimental activity without good guidance from ideas that come from theory and simulation now will not advance well. And without the advance of the experimentalists, theory and simulation will quickly stop. And so what are the possibilities to improve our is important. And I have pried Carlo Massimo, but he's too kind to have said that, to close his introduction saying, listen friend, we have put together community close, coherent, but they don't speak too much together. Be careful, don't slip to the complementary section, because then you are an idiot. Okay, I think this was what the workshop aimed to provide, and it's a pity if we fail. Sorry, Gerhard, I didn't want to forbid you.
No, I just want to sort of share this problem, because I'm working together with people in my university, which uses sort of nano holes in plastic, and they turn them into rectifiers, and they see even some kind of gating depending on the plastic material. And I was fascinated when I first saw them. So we have common projects, but we come from really sort of very different worlds, and we progressively come together. So for this workshop was fantastic, also just to see what is happening, because most of the communities, they don't even know of each other. So I didn't even know of things that I heard. So for that, the workshop was definitely not a failure, but the two worlds, solid state pores and ion channels, they are still also from the language, from the voltage, which is from the currents, we are orders of magnitude apart, but there are some common principles, and I'm sure this was also my last provocative slide was there are some common principles, because at the end it's all physics, which sort of we learn by sort of comparing the different structures. For example, the solid state nanopores, they are different when they have a conical shape, and the ion channels, they have a conical shape, and there must be a reason for this. I mean, in the one case we find it, the potassium channels are made by nature and they're conical. You know, they have a narrowing on one side and they're wide on the other side. The solid state nanopores, the good ones in their hands, they're also conical. There must be a common reason, and I think nobody has really yet sort of tackled this point.
Beautiful.
Okay. Can I elaborate a little bit on what Giovanni said? Yeah. So first of all, yes, some talks of neighboring communities may bring us out of our comfort zone, and indeed this is where something creative happens. So yeah, that's indeed a good provocation from Giovanni, as usual. So just to start from an example, I ask the panelists, but also people in the audience who can just contribute by unmuting themselves and showing their face. So my question would be, what have we learned from, for instance, years of studying selectivity in ion channels, which could be used in membranes for desalination, for instance, or for some smart technology that can address issues in blue energy or in water purification? This is just to make an example, to make it tangible, what Giovanni was suggesting.
I have an easy answer. From this meeting, I learned that I have to study more ion channel to understand my simulation in solid state. So I have a long list of paper to study on ion channel, because we observed in solid state nanopores in simulation think that I was not expecting about selectivity that maybe were discovered in the field of ion channel 20 years ago, and it was my ignorance to know. And so thanks to this meeting, I know what I have to read. And this is the only thing that I know, Alberto. In this moment, I don't have any more serious answer to your question.
May I raise a trivial question? And the question is that, is there anyone, I like very much what Mauro says, but it's personal. Is there anyone that has seen a crossed problem that could start a collaboration in between participants to the workshop? any one of the audience of people participating has been able to see that he would like very much to visit another friend that has participated to the workshop to start discussing something to learn, just to be provocative with Mark. As Mark Sansom, has Mark seen somebody that he would like to invite to his lab to try something in another field? It would be great.
Yeah.
Would be a success.
Well, we heard a very nice talk from I forget from Maya, was it, or on argon and the effects in simple in Gaia, sorry, on argon and effects in simple nanopores and on the water behavior, and I was immediately interested as to what that would do for the behavior of water in more strangely shaped biological pores. So I think, I think there is maybe not a dialogue so much in meetings because we sit in our own communities, but I think certainly I spend a lot of time looking at the nanopore literature to try and understand what's going on in channel systems. And I think there are ideas going back and forth. I mean, going back to what Gerhard said about the geometry of pores, there's been very nice work on water flow through aquaporins and trying to understand that purely in terms of fluid dynamics calculations. So I think there are points of contact between the two communities. But maybe it's more sociological problem. We hang out with our fellows. The biologists hang out with biologists, and the physicists hang out. Sometimes we're chemists, and we don't spend enough time together.
And also, another possible interesting question is, would anybody of the theoreticians, simulator or theoretician is the same to me, that have participated, be tempted to visit, just to say an example, Gerhard, to know something about his techniques so that he can understand better what experimental activity at nanometric level can bring to imagining interesting simulation? Also, this would be a measure of the success. And what Mark said was just warming me up. I am very happy to hear from you, Mark. That's great. Ignacio, systematically you close your...
I close my microphone because apparently I create noise, so I tend to close my microphone when I have to talk. So maybe we are already sort of like 20 minutes late. I think this has been a good discussion. Maybe because there is this pending question by still Blasco Morosco. Maybe we can pose this question, which is a bit more specific than the general discussions we were now having, which I think is one of the objectives of the workshop, as a final then we can conclude. After all, it's already Friday afternoon, so maybe Blasco asked about if they think that there are something fundamentally missing in the understanding of which is related to the relevance of the quantum level. So I don't know, again, that's a very general question. Benoit referred to it when he was talking about ab initio and in relationship to force fields, but I don't know if there are other aspects you think it's important to think about. I don't know if Mark Blasco is going to elaborate these points.
Sorry, I was having a bit of trouble hearing, but I think my rather feeble answer to the question is I don't know if we're missing something at the quantum level, and partially that's because the systems, at least that I'm interested in, are still beyond, by and large, beyond addressing at that level. But it's getting closer, and until we try, we won't know. So I don't know.
Okay, so that's also something there in the future to look at. Okay, so I think we can come to the end of this roundtable. Thank you very much, panelists and the participants, to ensure that there was a lively exchange of opinions. And I would like to close with this final discussion about the importance of bringing these communities together and to get to know each other, first of all, to understand what are the problems and possibilities. And hopefully, this will lead to more closer contact. Again, being remotely also it's a barrier to favor this initial contact among people that don't tend to gather together, as Mark mentioned. But let's hope that nevertheless, this has been very engaging workshop. We will see this new kind of collaboration in the future. Now that we come to the end of the workshop, I wanted to finish by I think I share the opinion of all the participants to thank Alberto, Carlo, and Antonio for the effort to put this workshop together, for creating this atmosphere to exchange and to get to know each other and to understand what are the interests and possibilities from these different communities. And I think we have to thank them because of the extra effort to have to prepare not only a remote meeting that I think has been successful, but the uncertainty of understanding what would be the shape of the meeting. I remember exchanging emails with Alberto if it had to be face-to-face, hybrid, remote, what was going to happen. So I think they have been making a strong effort to ensure finally this remote event is as interactive as possible with constraints. So I think we can give a remote applause to the three organizers. Thank you very much for your effort. And I'll give now the word to Alberto to give the final words.
Thank you very much, Ignacio.
Okay, so I don't know if you want to say closing words or just give it.
Yeah, very quickly. I wanted to thank first of all all the speakers that you see here on the screen, because this meeting has been so enjoyable, at least for me and for the group here, because of all of you. So that was great to hear different ideas. I think Giovanni is right in thinking that this should stimulate collaboration. Personally, I have many places where I would like to go to visit some experimentalists that have talked and given beautiful talks here. So from my point of view, this certainly helped. And I also wanted to mention, one second, because of course the presentation got stuck. Okay, that's nice. Okay, the presentation got stuck. So the next slide was not a slide, was simply, I would call, okay. Okay, if you see my screen, these are the people that talked, but I also wanted to thank Giovanni that again has brought back the spirit of this conference, and Ignacio that has led our roundtable, and Carlo Massimo, Carlo, Antonio, and Silvia, the ERC, Sapienza, and Silvia. But also I really want to thank them individually and show you their face. So I hope they are now participating, and we'll turn on the camera so you can see them. And so to the right of your screen, there's Antonio, in the center, Silvia, and then Carlo to the left. And they've been backstage, but actually it's their effort that's made all this possible. The last thing I wanted to say is that Giovanni is writing something else, so that the most important thing would have been to meet all of you. And so I hope to be able to see you in Rome in a couple of years. So we're now thinking of organizing a follow-up on this, and this time, hopefully, in presence. Thank you all for participating and giving so nice contributions to this workshop.